Does that make sense? Questions? So, I hope I haven't lost my Venn diagram. So this yeah, this is space, right? Yeah. Exactly. But you know the problem is we don't even know if P is not equal to P space. It's conceivable that all of this is just P. So forget P versus NP, we don't even know if P is not equal to P space. Right? Now you would have noticed that, you know, I drew this, okay, actually. If you think, what about non-deterministic P space? Right? A non-deterministic machine that uses polynomial space, so it's non-deterministic, right? So it has all these choices it could make. So this actually is equal to P space. This is not an obvious theorem, and this is called Savage's theorem. From the 70s, I think, yeah, I forget exactly when. From the 70s, actually says that non-deterministic P space is P space. So non-determinism doesn't seem to buy you anything in space, but it does buy you something in what we think. In time, it does make a difference. This is not obvious. How you like. There's no way that you're not going to look at this and guess like, oh, I think that's how they did it. Okay? So P space is equal to NP space. So that's Savage's theorem. But now you can ask, I mean, so we had tautology here, and we had SAT over there. Do we have some nice notion of P space complete problem? Right? So this is the complete problem here. And very interestingly and very nicely, there's a generalization of SAT that sits there. So there's a nice problem that is P space complete. Okay, so does this make sense, this picture so far? And, okay, so let's go back to the circuit. x1, x2 to xn, and this is 0, 1. Right? And so SAT is, does there exist x1 up to xn such that phi, oh, I'll just refer to this as x is 1. Like x bar is basically just the vector of all of those. Okay? So x bar is equal to x1 to xn. Now, yeah?
Wait, so if you were asking like the question like for the language to find all the possible like permutations where SAT would be satisfiable?
Not permutation, but inputs. Right.
Right, so would that be inside the like P space complete?
So, well, it's okay, good. So it's sort of it's getting there, right? So we have this notion of SAT, which is does there exist some setting which makes it true? We have a notion of tautology, which is for all settings is it true? But what if I mix them up? Does there exist a choice of x1? So for all choices of x2, there exists a choice of x3. So for all choices of x4, this thing is true.
Oh.
Right? I mix quantifiers. Okay? So I mix quantifiers. So for example, here's a question that I can ask. Does there exist an x1? So for all choices of x2 and x3, there exists a choice of x5. So for all choices of x10, there exists a choice of x7, so on and so forth, such that phi of x is true. Okay? So I mix quantifiers. Again, this is P space just by the same logic, because you iterate over all assignments and just check if this is true. But now it's not even clear how you would certify this to be true or false or anything. Right? This is actually referred to, this problem is called QBF. It's called quantified Boolean formula. Quantified Boolean formula. This isn't as crazy a problem as you might think it is. You might think like, why would anyone care for something like this? And it also comes up in sort of in trying to verify code. So it's actually sometimes two levels of alternation are useful to think about. There exists x1, let's say xk, so for all xk plus 1 up to xn, something is true, or something simple here. Does that make sense? Like once you set all these variables, you're doing something simple. But you're trying to understand, is there a setting of variables of this kind so that this is always true? Does that make sense? So think about, you remember this question that I asked about, is the minimum sized circuit that multiplies to n-bit inputs. Right? I could say, is the minimum that multiplies to n-bits, or does this have at most, I don't know, k gates? And this is a natural question to ask. The minimum circuit that multiplies to n-bit inputs does have at most k gates. If you think about what this is, you're saying, does there exist a circuit so that for all inputs I fed to that circuit, the circuit computes the product properly? Does that make sense? The there exists is over the circuit, the for all is over the inputs. That question, does that make sense? Yes, no? Yeah? So that would be something that is a QBF. It's quantified Boolean formula. But it's only 2 levels. But now I could do even more switching if I need to. So actually the one at 2 levels is called sigma 2. But that I doubt that we have time for. So QBF is p-space complete. QBF is p-space complete. And so in our face over here, you have QBF. Yeah?
So do we know if it's in NP or not, or we only know it's in P space?
We only, if QBF was in NP, then NP would become equal to P space. I mean, so okay, so this is where like once you know all these facts, you start chaining them together. Say if QBF was in NP, then actually NP would become equal to co-NP. Because okay, if QBF was in NP, it means that for any problem that's in P space, you can do it through NP. But the hardest problem in NP is SAT. And co-NP is in P space, so co-NP would become contained in NP, and the thing would collapse. That would be huge. It would be huge if any of these things were to become equal. So we don't even know any of that. Yeah?
Is there anything that goes in the nose?
This? Yeah, we'll get there. That's, as I said, that's cryptography. Like, that little portion over here would seem like, oh, it's like, cryptography is like buried in this part. So, okay, so, now at this point there's actually 2 things you can do. You can go one step higher, you can go one step lower. So I'll show you both, because they're both kind of both. So do you follow this so far? Okay, so now let's look at P space. I'm going to keep the S unbold because I don't like my bold S. It's not, it doesn't look so nice.